Greetings, wonderful students of physics. Captain Rod here. I'm making a video here to help you out with three of your homework problems here. So we're going to talk about numbers 18, 19, and 20. Starting with number 18. So it says a skydiver jumps out of a helicopter and falls freely for 9 seconds before the parachute opens. So an important thing to realize, the problem has nothing to do with the helicopter. It's about the parachuter. So start with a picture. Here's my person. And under the influence of gravity, that person's going to accelerate down, and that's why these distances between these dots are getting bigger and bigger and bigger. Just a little reminder now, the dots, these are what are called motion diagrams. Imagine like a digital camera taking snapshots, click, 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 and then superimposing them. And I use the dot to represent the person just so I don't have to draw the person over and over and over. But these dots are getting bigger because the person, as time goes on, they're moving faster and faster and faster. Right now, with these problems, whenever you can, draw a velocity graph. Right? And what is that? It's a plot, typically, of velocity against time. And remember, velocity describes how fast something's moving and in what direction. Right, so we're going to start our time here at t equals 0. Now, right when the person jumps out of the helicopter, right at that instant, they're not really moving yet. I mean, gravity hasn't had time to act on the person. So we're going to call that time 0, and they're not moving yet. So when the time is 0, like left to right on this graph, velocity also 0. Now, sometime later, right, we don't, actually, it's given in the problem. Mine says a delta t of 9 seconds. 9.0 seconds. Yours might say a different number here because I've set this up to randomly generate values. So when we plot that, we come over here and we'll go 9 seconds, and we don't know a velocity. So what we'll do is we'll just put a dot here to represent it, because even though we don't know it, we do know they are going to be moving. There is some v there. We just don't know how fast yet. And then we will make our standard constant acceleration assumption. So on our graph here, important thing to realize, right? So, whoops. This distance is the 9 seconds. This distance represents the unknown velocity. We don't know what that is. Right? The coordinates here would be t and v, or 9 and v. Right? So there's our velocity graph. Now, these graphs, remember, have two important properties, slope and area. Let's start with this. The slope of this line, remember, slope is rise over run, right? That's a change in v. And the run is a change in t. Right? This is the acceleration, and because this person's free falling, we would expect a numerical value of 9.8 meter per second per second. The delta t is given in the problem. So what you do here is, put your delta t in and calculate this, and that will tell you how fast the person's falling. Now for part B, where it says how far did they fall? Well, once we have this velocity graph, and hopefully you've seen my other videos on how to do this here, the area bound under this right here will give you the how far. I usually call this like delta x. And this is a triangular area. It's equal to 1/2 base times height when you find the area. So that should get you through number 18. Okay, 19. So believe it or not, 19 is virtually identical. You look in the picture and you'll notice it says acceleration is 1/2 g. What they're saying here is to assume the acceleration is approximately 4.9 meter per second per second. That's half of the 9.8. Other than that, this problem's identical. Draw a velocity graph, probably assuming that at t equals 0, the velocity is 0. That graph will look very similar to this. Write an equation out for the slope, which looks like this, except that instead of 9.8, we have a different value for the acceleration, and that will allow you to solve for the change in velocity. And then the how far, again, area under the curve. 18 and 19 are virtually identical. All right, number 20. So number 20 says to find a drag racer can go from 0 to 210 mile per hour in 8.8 seconds. 0 to 210 mile per hour. Now, this number may be different on your homework. This is the one I have, but again, I've set these up to give random numbers to different people. And it just says to calculate the acceleration in G's. Now, I'll explain what the G's mean in just a moment. Let's just start with find the average acceleration. All right, so how is acceleration calculated? It's equal to change in velocity over change in time. Now, your change in velocity, right, is your final velocity minus your initial velocity. However, the units are in mile per hour. What I recommend is start by taking that number, the 210 mile over hour, and convert it to meter per second. Right, so multiply by, let's see, we would want what? Miles in the bottom, meters up top. Right, and there's 1,609 meters in 1 mile. Then next conversion factor to get rid of the hours. Hours up top, seconds in the bottom. 3,600 seconds in 1 hour. So get this done, you're going to get a number. That number is going to represent your change in velocity in meter per second. Then just divide by the time also given in the problem, and you're going to get a numerical value. Now, that number will come out in meter per second squared, or meter per second per second. Let me talk about the 2 G's. Let's say we had an acceleration of 19.6 meter per second squared. Now you'll notice that's equal to 9.8 times 2. That's what you would refer to as a 2G acceleration. The numerical value is roughly, is 9.8 times 2. A 30 meter per second squared, see how that's roughly 3 times this, that's referred to as a 3G acceleration. So anyway, long story short, when you get this number, divide it by 9.8, and that will tell you how many G's that is to answer that question. So that should get you through those problems. I hope that these videos are helping you out. And again, don't be afraid to call or email me if you need anything. All right? Have a great day.